Garchi, and also he stayed in Brazil. So now he's in Valencia with a GENT grant. And today he's going to speak about simulations of supernova explosions. So you have the floor, please.
Okay, thank you very much, Daniele, and thank you very much for inviting me also to giving this talk here today. And I hope I can tell you a bit about what we're doing in Valencia. It's now a nice time to be there because also the local government, they published, they started this new plan, which funded my position. So I'm really grateful also to them. And I'm working on this project of long-time simulations, which I started in a postdoc with Thomas Janka in Garching and Anna von Matanarat, who was a postdoc also in Garching. And I'm working now on this with my student, Beatrice Giudici. And what we try to do is to do the long-term simulation of supernova. So we are not interested in the very first seconds, but we want to bridge the gap between the explosion itself and to the time that we can observe something from the supernova. And how we do this, I hope I will guide you through my talk and tell you why we do this, give you some motivation. And what is interesting, what are core collapse supernova in a short review, just to remind you what I'm talking about. Talk about some of the two most interesting observations we would like to explain with some of our models, which are just very nice to see and to compare to. And then I will tell you how we will do it, what are the numerical models we are using. And then, of course, I will tell you the results, what happens during the explosion, the different phases of the explosion when the shock of the supernova gets revived by the neutrinos, how it propagates through this progenitor star, and what happens then at later phases once the shock breaks out from the progenitor until the homology is reached. And in the end, I will conclude my talk. So please, if there's any questions, also please ask me during the talk. I think there should be enough time. It's not too densely packed. So core collapse supernova, they are the end of a lifetime of some massive stars. Depending on the mass of the star, you can have different outcome of the life of the star, and they also live different times. But what we are talking about are stars which are heavy, which are more massive than 8 solar masses, and probably less massive than 40 solar masses. But this upper limit is not very sharp because it also depends on the details of the stellar progenitor and how the explosion goes on. But we are talking about the massive stars between 8 and 20 solar masses, which end their lives as supernova, and which then leave behind maybe a black hole or a neutron star or a supernova remnant. So there are different possibilities here, but we are talking about these massive stars, which can be either blue supergiants, which then pass through a red supergiant phase, or blue supergiants, which explode. So what happens during a supernova? At the end of the lifetime of a star, when he has burned all his fuel, it will have created a very strong, very heavy iron core, which is surrounded by some other layers of the star, which have this kind of onion shell structure, which we can see here with more and more lighter elements if you get closer to the surface. And in the center, we have the iron core, because iron is, of course, the most stable element we can reach by nuclear fusion. The scale here is not the drawing here is not to scale, so you have to imagine that the iron core is really very, very tiny compared to all the other layers. And everything what happens in the iron core is very, very fast to all the dynamics which happens in the outer layers. What happens then? At one point, when there's not enough material to further burn, you lose the pressure. You have less pressure support to the gravitation, and at some point the core gets so massive that some of the electrons also get captured by the nuclei or by the protons, and such that you also lose this pressure support, and the star starts to collapse in the iron core. And this will lead to a collapse of the entire star. So we see that the inner layers of the star start to fall into the center. All the material falls, the iron core, the center of the iron core gets more and more compact until we are reaching the densities of nuclear densities. At this point, you cannot compactify the matter further because the degeneracy pressures of neutron doesn't allow you to compress it further. And you will create a stalled wave, or the material will bounce back, and you will create a shock wave, which then tries to move outwards. However, this shock wave doesn't have enough energy just from the infalling and bouncing back. There has to be some mechanism to revive this shock wave. In the center, you will create a protoneutron star, which has these densities of the nuclear density, roughly. And we need to revive this shock. How do we do this? Depends a little bit on the model you wish to study. In our case, we think I'm talking about the neutrino-driven mechanism. So what happens is the matter which is falling in gets heated up by the neutrinos, which deposit some energy. The neutrinos come from the protoneutron star, which is very hot due to the inflow, to the compactification, and the neutrinos leave this region and heat up this material here. So you're steering this by kind of heating it from the bottom. You create a lot of convection, which allows you for the matter to spend more time here. And the more time you spend, the more the matter can interact with the neutrinos and the more energy you can deposit. And at some point you will deposit enough energy and this shock wave can be arrived and will move outward and propagate through the progenitor model. And this is then when the explosion sets in. We can talk about the supernova. When there's not enough of this heating, it may also be the case that there's too much accretion, when the star is too massive, then everything collapses and you will end up with a black hole and you will have something like a collapsar maybe. But we are talking about supernova. So what we see here, the shock will propagate outwards. Now we are in the silicon layer in this model. This will go further out, now to the oxygen, and you will create up heavier and heavier elements also by nuclear burning. In the shock front, you're burning also material. So we create heavy elements which move outwards, very asymmetric, which is something very important here. Very asymmetric due to the explosion. And this will propagate through the progenitor and will hopefully tell us something also about the progenitor structure, how this happens. But I will tell you a little bit more about this also during the talk. Okay, so what are then the observations we have from these supernova explosions? What can we observe? Ideally, we would like to understand what happens during explosions, so in the very center. But this is very hard to observe. You can imagine you have many solar masses of matter around this central part. So it's really hard to understand what's happening inside. One idea would be to look at neutrinos as have been detected by supernova 87A, the closest supernova we had in the last decades. Or gravitational waves would be also amazing to detect them because they would open us a window to look directly into the supernova engine. However, we need a galactic event for this. And it's very long waiting time for the next event. We don't know when this happens, so we need to look at very later observations like the light curves or the spectra of supernova. But this happens actually only when the explosion has propagated out of the progenitor, which depending on the model can take up to a day actually. So this is a very long time and doesn't give us direct information on the explosion mechanism sometimes. It gives us a lot of information on the environment, on the progenitor star, but on the explosion mechanism, it's a bit hard to get information from these more later observations. Oh, okay. So what can we use then to get some idea about what's happening in the very core of the explosion? So many people here are working on the compact remnants of supernova, which are the neutron stars or black holes, but of course neutron stars are much easier to observe. And what can we infer about them, from them about the supernova is, for example, the rates of supernova. If you count the neutron stars we see and have the age of the neutron stars, we can estimate how many supernova happen, for example. Or we can see the kicks and the spins of these neutron stars and see if they are somehow aligned or misaligned. This also gives us some clues about what's happening during the explosion itself. And the other thing what you can look at are also the young supernova remnants, which are the gaseous remnants. They are just a matter which is ejected around, sweeping up also some material around the neutron star or around the progenitor star. Like for example, in this example, we have the neutron star in the center and all the matter around is being shined, or the neutron star shines on all this matter by its pulsar wind in this case. And this we also can connect to observations. And here we see very nicely also these 3D structures in these models. And this is what we would like to explain with our model also to understand how the 3-dimensional nature of the explosion. If you can get some information about what's happening during the explosion by looking at the later phases of the supernova remnants. And of course, if you have these information, this will also have an influence on the spectra and the light curves. So up to recently, these have been mainly calculated with 1D models, but one can imagine that the viewing angle may have significant effect, and also the different distribution of the elements in 3 dimensions can influence the spectra especially very significantly. So one of the most interesting examples we're looking at is the Cas A remnant, because there for the first time we could see really nicely the genuine 3D structure of the ejecta and of the explosion itself. So for example, one can look at the high ratio of titanium to nickel 56. one expects from nuclear burning that these are produced in the same processes, in the same burning processes. However, if you have a high ratio of titanium to nickel, you know that something has to be produced more in some more denser regions than others, so it cannot be spherically symmetric, the explosion. So one can look at light echoes, which was done in 2011. So you also see that there's different velocities in different directions. You can look at some jet-like features in X-ray and optical. There's some, if you look now at, for example, some different combinations of X-ray observations, we can see also some bubbles in protrusion, which I will show in the next slide. And you can also reconstruct different elements. And then we can really nicely produce some 3D images of the supernova remnant, where we see here, for example, the iron in red and this the titanium in blue. And one question is, I just said that titanium is usually produced where we have nickel, and nickel decays to iron. So one would expect to have titanium and nickel and iron in the same area of the remnant. But here we see there are some correlation between the nickel and iron in some places. But here in the center, where we have a lot of titanium, emission from titanium, we don't see nickel. How this happens? Okay, in this case, it's something very easy because the titanium is decaying radioactively, so we see all the radiation coming from the decay. The iron is a stable element, so it needs to be excited. So it needs to be shock heated, and that's what we see here. That's the part of the iron which is shock heated. And we suspect that there's a lot of iron still in the center, which is just not heated to the temperatures that you can emit in the optical lines. But there's something very interesting here, like this jet-like feature, which is very hard to explain. So this we see, for example, in silicon and magnesium here, but it definitely shows you that the explosion is not spherically symmetric. Similar things can be done in different observations. Here we nicely see now the iron in green, which is like pushing through some shells of the lighter materials. So we find iron further out than, for example, in red, where we have argon, which is a lighter element. So we see that some of the iron is further outside. So this is something we need to explain why this happens when you think that the star has this cellular structure. And can also go to the other very famous supernova remnant, which was a supernova in '87. So it starts to be a remnant in these years, because we are now being able to observe different elements. Like here, for example, the silicon and the iron, and we see really again that it's not spherically symmetric. There's really some deviations from spherical symmetry, which are important, and this we have to explain. And we hope, with the kind of structures we observe, to be able to draw some conclusions on the explosion and also on the progenitors. Like here, we can also now look on different molecules where we have H2 and hydrogen. Hydrogen here. And on this side, we have then the carbon monoxide and silicon monoxide. And these are then things we can try to compare to our simulations and see if we can reproduce the kind of structures we observe there or not, depending on the model. And that's the final goal of these long-term simulations we have here. Okay, how do we do this? We have a hydrodynamical code with which we can follow the evolution from the explosion until the very late phases. We have some features which make this possible to go over many orders of magnitudes and densities and temperatures. We need special equations of state combined to each other. We need a nuclear network to follow the burning in the shock front, for example. We need some neutrino transport. In the model we are using here, we have a very simplified neutrino transport, which is fine if you look at the things we are interested in and how the dynamics evolve. We can tune. The nice thing about our neutrino transport here is that we can tune it to observations. It doesn't tell us about how exactly the explosion works, but it gives us a feeling how the explosion acts on the hydrodynamics on the matter. If you want, I can elaborate a bit more on this later, but the issue is like we don't have the most sophisticated neutrino transport, but this gives us the possibility to evolve on a time scale of up to years. If you want to do this with the more sophisticated simulations, you do the simulations of 1 second of the explosion in a time scale of a year you need on the supercomputers nowadays. So it's very long, and you cannot do this in a systematic manner. And for the later time evolution, we also include the beta decay, which we will see has a significant effect on the structures as well. Okay. Good. So then let's have a look what happens in the beginning of the phases. So I will show you here now a video of the entropy, which shows you very nicely in the first second or the first fraction of the second how these initial burning and boiling happens in the center. So you see really nicely, it looks very stochastic. We have different plumes rising and mixing up here together. And at some point, so now we see that the structures don't change and everything is expanding. So we zoom out at the time that the matter is expanding. We see here the scale. And now these structures, so these asymmetries, they're imprinted on the explosion. This happens when the star explodes. And as we will see, these structures, they will survive until very late. They will change its shape during the propagation through the progenitor, but they will be still imprinted in the very late time observations we could observe, like in Cassiopeia A, for example. So what happens then at some point, really, the explosion starts, everything expands, and there's no boiling anymore. You see that the structures, they don't change significantly. So you maybe see some acceleration of some material which is catching up with the shock front, not with the shock front, but with a fast moving ejecta, but there's no change of the structures in this. And we have the time of now 1 second, so that's usually the time when the explosion really sets in. Now the next steps is to understand what happens once we have this beginning, which is a little bit stochastic because you have to be boiling, you don't know exactly when the explosion sets in. But this defines where these initial big plumes arise during the simulation. And also in this very early phase, maybe up to a few 100 seconds, you define actually what happens to the compact remnant. So what happens if you have a lot of ejection of matter to one side, and on the other side you have the matter staying close to the neutron star. This matter which is closer to the neutron star will pull the neutron star in its direction. It's just a gravitational pull, which is called also then the tugboat mechanism. So you have the matter here pulling the neutron star to that direction, which then defines the neutron star peak. And we can see this very nicely in this very asymmetric explosion, for example. This is one of the models we simulated. We see that the neutron star is accelerated exactly opposite to where the most of the matter is going. Here we see, I will show you more of these kind of plots. This is the surface of the nickel. We use nickel as a tracer, which we show the surfaces because this is very high mass element, which is also important for the decay because as it's radioactive, it decays, and therefore the structures which contain the nickel tell you something about the structures of these higher masses. And also, of course, the initial phase also determines how fast the neutron star is spinning in the end. Yes, in these models, yes. Yes, exactly. In our models, yes. But of course, you're completely right. This is very important for the complete picture. And we are working to produce now also models in 3D just before the explosion to see that maybe also convection in the progenitor star. This is also can also be very important. For example, it may create some asymmetries which allow you for an easier explosion in the beginning. And then these are things which are under investigation at the moment.
What is the origin?
In the moment, it's just these boiling of the neutrino heating mechanism because you have a lot of convection and you can have different instabilities, polyhydrodynamic instabilities, while the shock is stalled. And during the first second, you can have these, the easiest maybe is convection, we have these convective bubbles. And once there's enough energy deposited, the bubbles, what are there at the moment, they will expand. So it's a bit stochastic depending on these instabilities which you have during the explosion. So the next step is to consider what happens if now the ejecta and the shock, they move through the progenitor and interact with the mass of the progenitor. And what will happen is you have different slopes of the density in the progenitor. And whenever you, so everything depends on the radial dependence of the density structure of the star. If you can approximate this with some index n here, and this index n is larger than -3, then we have deceleration. The matter will get decelerated. When the index is smaller than -3, so more negative than -3, is meaning that it's steeper here, then we always will have acceleration of the shock and also of the matter in this region. And this will determine how the shock and the matter will propagate through the star, and will also determine that we have some instabilities. And this is very important as we will see the Rayleigh-Taylor instabilities. you will see very nicely how these structures, these huge bubbles, they will fragment into small Rayleigh-Taylor fingers, which are very characteristic for this kind of instability. And these are very important for the mixing of the ejecta. As we have seen also what we have observed before, for example, for 87A, I showed you some pictures of carbon monoxide and silicon monoxide. So that's important to get these elements together and how they are distributed in 3 dimensions. So this will be defined mainly by these instabilities which are happening through the propagation of the progenitor. And you also form shock at interfaces. You form reverse shocks, actually. If you can imagine, you accelerate the material, for example, here, then you slow it down, you can imagine that there will be a reverse shock which will propagate into the material. This happens at the different interfaces in the neutrons, in the progenitor star, but also then in the external medium. If you go to the interstellar medium, the same will happen. We'll create another reverse shock which also will propagate inwards through the matter and will change also the structures we will observe. There's just some more details about what's happening. This shows you that always when we are at one of the shell interfaces, which are indicated here by these dashed and dotted lines, you will have an increase of these parameter, which is a measure for the instability. And okay, I think I will skip this. Just that we will see here, there's a reverse shock which builds up here, first travels a little bit outward and then starts to travel inward again. And in this case, when it starts heating the central region, it will be so compact that it kind of self-reflects because it heats up the material in the center, that it starts to expand again, and there's a shock wave then moving outwards again. So that will be also something influencing the matter in the exterior. This second shock wave passes through the ejecta here. Okay, so there should be a movie from this. This is something quite recent. That's why the movie is a bit not very smooth yet, but I think it shows you very nicely what's happening. So these are now, this is now for the same model, but I'm not showing the entropy as it was in the first movie. I'm showing now these surfaces of the nickel. So we see where all the nickel is concentrated within these bubbles. And we see how this will change during the evolution. We see that the fastest nickel is outside. I show the velocity. Now we see how these fingers, they fragment, they extend. Oh, sorry. Go here. So these fingers extend, they fragment into a little bit smaller fingers. And what will happen now is that one of these reverse shocks forms and will compress the structures a bit to the center. This we see now, it compresses the material. We see actually now that there's some material outside with lower velocities than here. So red is the highest velocity. So these orange colors is lower velocity. So we see that there's some reverse shock compressing the material which is further inside. Here we see now that pushing through this material, we are subject to some instabilities. We see how the matter here fragments. Also these long fingers, they are now more fragmented than in the beginning. And now we pass to a second phase of Rayleigh-Taylor instabilities. We see that this fragmentation continues further. We see much more extension to the outside. And then just stop here again, if I can manage. Okay, anyway, we will see this in the next slides again. So here we see the same for a different model, where I showed some characteristic pictures of the different stages of the evolution. Here we have the initial phase just after the explosion, so 1.7 seconds, where you see now all these bubbles, which are just from the initial hydrodynamic instabilities, which arise and the expansion starts. Then you pass to a first stage of the Rayleigh-Taylor instabilities, where these big plumes, they fragment into much smaller fingers. We see here again very nicely in this model the reverse shock, which is almost spherical, penetrating now into the center of this material, compressing the central part. There are some fingers sticking out, and these now in the next phase of Rayleigh-Taylor instabilities, they start to fragment further and to elongate, which we then see here at 7,000 seconds in this model. We see that the central part gets compressed further and further, and this is still happening all inside the progenitor star. We have, and what's happening after after roughly 1 day, so after this stage, it starts to become important. the decay of nickel becomes important. The energy input to the decay of nickel becomes important because you start to have an additional energy source, which makes the structures, we have a lot of nickel, to expand with respect to the other structures. And that's what we can see here for different models. We see that the volume, which is containing the nickel, is firstly here for all the models. Initially, it's decreasing because the reverse shock is compressing it. It's slowing down when it gets in, when it expands into the ejecta. But then after roughly 1 day, it starts to increase these volumes. And this is when you put some additional energy. So these fingers first get a little bit compressed and then they start to expand again. And as we can see here, we have so the same pictures here. Then we see the very elongated fingers. And after a while, you see that they expand in size. So they really start to merge here again. Also the velocity increases slightly, which you cannot see too much in this figure, but it increases up to 30%, depending on the model. You see, especially in the center part, where you have a lot of nickel, you see now that we are going from blue to more whitish color, so it's accelerating all these material in the very center. Okay, we can look at this also in another video now for different models. We now see the reverse shock compressing the material, the central material is compressed more, these fingers stick out. Now we see very nicely in this model, we have very strong asymmetries in 3 prominent directions. We have one in this direction, one in this, and in this direction. And we see very strong, these very large asymmetries. Now this is at around 10 days. Now it continues. We see now that the energy deposition in the center, also these reflected reverse shock, make an expansion of the central bubble, and we also see nicely how these elongated fingers, they expand again, and especially in this region, we see how they merge again. Yeah. Okay, I think enough. Okay, this is now to compare different models, which have very different morphology at the end of the simulations. This is now at roughly 1 year when we stop the simulations, because with the physics we have at the moment in the code, this is the point we reach homology more or less. So we see in this model, for example, it's quite asymmetric, but in a way that it's quite isotopically distributed, these different fingers. Here we have like these 3 regions when we have the fingers. Here we have like maybe like 5 or 6 in the back. And this model is very, very symmetric still. So in this model, we know, for example, all the symmetries, they didn't have time to grow. And the reverse shock was compressing the model very effectively, such that there was no time for the Rayleigh-Taylor fingers to grow. Yes, please. Yes. Yeah, that's very late. That's after 1 year of evolution time, exactly. Yes. But that's exactly the structures you see in the first second in the explosion. So that's the nice thing. That's exactly actually how we would like to get information on the explosion from the late structures we observe in the very late phases, even in the supernova remnant. So there's some connection between these asymmetries and the very initial asymmetries. Yes, sure. Well, if you have a black hole, you don't have an explosion. You probably it should be very fine-tuned to get some ejecta coming out. So usually you have it in neutron star in these cases. It's very hard to have a black hole and an explosion. Okay, that's another video now. It's a density where we saw where we now see a slice of the evolution. Which is now these structures where we see this one very elongated Rayleigh-Taylor finger. We see that it's overdense at the moment, so there's a lot of nickel and heavy elements here which have penetrated through these shell-like structure which we have seen for the progenitor. And we will see how this now will expand and will create actually an underdense region here and overdense borders of this region. So that's also something we would like, which is observed in the models in Cas A, for example. You have these bone-like structure which seem to be hollow, and that's something very nice. Now you see that after a few days, this starts to expand the center of these regions, also the very center. They become underdense with respect to the surrounding, and the borders of these fingers and everything becomes overdense. And how this looks, I just have now a different color scale where you see this nicer. So there's really no change which can be up to a factor of 100 of difference of the density in the finger and the finger wall. And this is important, of course, for processes. If you want to make molecules or something, you need high densities in these regions. You need to have a lot of different elements mixing up together. And this is something you may observe in Cas A. You need to make this connection still in the future, because then if you want to have molecules or something, it's getting more and more complicated. You need to understand when you can form molecules or even dust in the end. Just also to show you, to convince you that these asymmetries we observe in the end, they are really related to initial asymmetries. We see here the nickel surface, the radius of the extension of the nickel surface at the beginning of the simulation at 1.3 seconds, when this model starts to explode. So this is color coded, and the black circles here, or the black contours, they are the asymmetries actually at the late times. So you really see a very nicely, they're very nicely matching each other. So we really can say that the asymmetries observed in the end, they come from the asymmetries which happened in the beginning, which are connected to the explosion mechanism. And now we can start to compare our simulations also to observation. Yes, please.
Sorry, so what is the iron core in that?
The iron core is exploded. There's nothing in the center. There's a neutron star in the center left, which has roughly the mass of the iron core, but everything else is exploding. So yes.
The remnant is there. I mean,
The neutrons, yes.
might have left already, because I don't know.
Where the kicks are usually like hundreds of kilometers per second, so the time scale we are looking at, you don't see them moving yet. You don't see an influence on the remnant yet. If you would look in the time scale of 100 years, thousands of years, there may be an influence, sure. Or there are some observations of pulsar wind nebula which are really deformed. They can see bow shocks of the movement of the pulsar in the interstellar medium, but this is much shorter time scale. So there's no time for the neutron star to have a significant influence on the ejecta here. Just to say, we cut here the central part just to accelerate the simulations, because there's a very little mass in the central part, and if you would try to simulate this, this would just be impossible to simulate in today. So that's what we see here. So that's not the size of the remnant or something. That's really just what we cut out here. Yeah. Okay, now we can start playing games, comparing to observations. There's like these observations of 87A a few years ago, where we see the carbon monoxide and the silicon monoxide, and we have the four models, which I have shown you before already. And we try now to find some matching of some slices. So that's now the real observation here of 87A on the left, and here on the right, we see we just multiplied the densities of carbon and oxygen, just to see if you can roughly reproduce the structures. And what we see here, well, this looks very nice. So you can say, okay, there's no contradiction. But if you look here, for example, in this model, this looks very different. So roughly the diameter is the same, but the scale of these clumps here in this model, it's very different compared to this one. So we can say from this simulation that probably this progenitor with this explosion cannot explain 87A. So none of these models was done perfectly to explain 87A. So there's no matching or something like this. But we can already say that this model is very unlikely to have been responsible for an explosion of 87. And the same holds also for the silicon monoxide here, where we see similar structures. If you look at this statistically, we can analyze now the clump size and the clump separation and do some other statistical analysis of our simulations and try to compare them. But what we see here, for example, we have the dashed black line, which is the data. We see just what I just said. The clump size, for example, of this one model, of the N20 model, is much smaller than the one we observed. So it's really hard to imagine that this model could be responsible for explaining 87A. And also for Cas A, the simulations we have done have been continued by some other group, which are able to calculate until later, also to produce some nice images. Also some real observations, they are able to calculate the emission, which we are not with our code. But here they show, for example, now the distribution of iron in red and silicon in green. And we could look and compare this here. Unfortunately, it's exactly the opposite color coding. So the iron here is in green, which is red on this kind of plot. and the lighter elements are in the reddish colors. But we see really nicely that we get the same kind of structure. So the iron is getting out here, and the other elements are like a crown around this iron, which is pushing through these different shells. So this tells us really that we're on a good track to get something about the explosion by comparing the models to the remnants here. However, which we cannot explain easily and which is still a big question we need to answer, how we can make these jet-like structure in Cas A, for example. Because if you would imagine that some explosion comes from the very center of the star, you would expect to have some iron in it, because the iron is what you have in the center. And in this jet-like structure, you don't see any iron. That's something we need to understand. So there's no real consistent picture how this can happen actually up to now. Good. With this, I would like to conclude also. I would like to give you some things which you may take home from this talk, that the supernova in Sweden, we know that, no, we not know, but it's very obvious that you create the asymmetries during the very first second of the explosion. And this shapes you very strongly, the asymmetries. But these asymmetries, they are still observable at late times. They are shaped by the propagation to the progenitor, also by the energy input due to the beta decay, but there's still some connection of the final asymmetries with the initial asymmetries. The different shocks, they may accelerate the ejecta. Also the beta decay in general, it accelerates the ejecta, can be up to 30% depending on the model. If you have some very compact model, it can accelerate quite a bit. And it will also create these density enhancement, which are probably very important for the observation of the different elements and the different molecules or even dust in the late times. The homology, this means that the fine structures don't change, so there's no additional inflation, but everything is just expanding with radius in this time. This should be reached after roughly half a year or 1 year, depending on the model. And then the next steps is, or I mean, all what we have here shown here is very nicely, but it's very qualitatively. So we say, okay, this doesn't look like this, so we cannot reproduce this. But what we do next is also to compare this quantitatively, to say how different are the models, or what is missing in this model maybe is compared to the other model. And for this, we need some new methods to analyze them, and also to do many more simulations now. And that's what my student is doing. She's now doing creating a library of red supergiants. We have many blue supergiant progenitor models. And we need to, maybe the idea would be to see some systematic differences between different classes of progenitors, and to learn something how this affects the explosion itself. And as you have seen, there's also very nice observations at the moment coming in 3D. There's now James Webb telescope is also up there, which will also give us some very nice data. So it's a very, very nice time and very timely time to really compare the simulations and the observation in 3 dimensions. And we have now the tools, and we have to do it now. So thank you very much.
Thanks, Mika, for the very nice talk. Any question? Yeah.
This is some optical ejecta. So this is lighter elements. That's the same. Yeah, that was Cassiopeia A. That's observation of Cassiopeia A, but showing you different things. Yeah. So the yellow dots here, this is just the optical observation of Cas A. Different things. No, the blue is the titanium, and the green is silicon mainly.
But to my eyes, it's like, you know, the yellow, there's color with the structure.
That's true, actually. Yeah. So you have lighter elements around here. Yes. The big question is why we don't see, for example, nickel in there or titanium or something of the higher elements. Yeah. That's a good question.
Questions?
So, as we need to the simulation, have the progenitors file, right? So, I'm wondering what happens in cases of more exotic structures, because I suppose you take a normal profile of the string stuff, right?
Yeah.
Has anyone seen what happens in final interaction?
Sure, yeah. So there's also something, some models when you have, for example, like something like here, So when you cut the hydrogen envelope, for example, that's something similar to binary interaction. If you just take away exactly the strip the hydrogen, and then this then the thing would be like then you would cut off some of the phases of the Rayleigh-Taylor and the instabilities, because you would propagate into more dilute medium. So you would conserve some structures which are a little bit earlier. So you skip. Doesn't work. It just takes too long. So for example, you would then stop at a phase like this, just expand and not go through these additional phases, something like this. And you would be much faster, for example, because you have less mass through which you have to propagate, which you have to accelerate.
I'm thinking also some words and stuff like for example, have a treated material from a combining star using their sequence.
Yeah.
Or maybe chemical homogeneous stars.
Yeah, that would be interesting to check these things, of course, but we don't have observation of these stars. That's why they are not on the top priority list. But it's something interesting to see, because surely all these structures they have very strong influence on how the instabilities operate, and they determine you if you have a more spherical or more asymmetric explosion, like in the different models here. We have also done, for example, low mass models, which explode easier because they have less material falling in, and they are almost completely spherical. They're even more spherical than this model. So it really depends on what kind of progenitor you put in.
Let's say that you can manage to like run the models like on the time scale that you like want to get. Wouldn't it be the most important thing after that? Like after that?
So I mean, the idea is to compare to observations, and to do this, one needs to do more physics. We stop now at 1 year because actually a bit before, which I was not telling you, there are some new physics which get important. So you have the heating of the bubbles, they start to expand. But once they get optically thin, they will start to cool, for example. So you need to put in some more physics. So this 1 year, I would say, is at the moment the time where we can trust with our simulations. The other group which I showed you, the simulations of Cas A, in the end, they have some more physics in them. They can calculate, for example, the synchrotron emission and everything like this. So they can really reproduce very nicely for 87A the emission spectra and stuff like this. And they can even predict how the ring of 87A will be illuminated or will fade with time and stuff like that. But the idea would be to get some comparison to the observations. So that are the next steps to make this comparison. So I think in the progenitor itself, it will not have a too strong influence because the magnetic field is not strong enough compared to the dynamics of the hydrodynamics. At late phases, it will be important, sure. And for things, if you would like to see cosmic ray acceleration, you need magnetic fields. If you model these kind of things, you need it definitely. But for the structures in morphology, it's probably not that important. So for example, it will be important because it keeps you, so which I haven't shown yet is, for example, the interaction with the reverse shock from the interstellar medium, which happens at much later time, not at 1 year. It can happen at hundreds of years, usually like in Cas A, where we see this interaction where the reverse shock propagates through the ejecta. And there it may keep all the matter a bit more stable. So it's not substrate. The Rayleigh-Taylor instabilities, they don't go as fast as they would without the magnetic field. But that's the major effect. And in the different group I showed you, they have magnetic fields actually included. But maybe to add also, if you have really strong magnetic fields in the explosion, so you have a really fast rotation, really highly magnetized star, this can be very different. That's some colleagues in Valencia, they are doing these kind of simulations, like Martin Gabler and Rayleigh. And we are very interested in continuing these simulations now until the late phases to see what would be the imprint on the late phases, on the supernova remnant over this. Because then you have these jet-like emission along the axis, and this probably will have strong influence.
conclude that densities, expands, at least these stages, it's not very relevant.
Yeah, it's too early. That's too early because also the energy you put in is not, and there's not a lot of mass swept up. Yeah, at this stage is 1 year, up to 1 year, you don't need to worry. The important thing is, of course, a little bit the gradient of the wind, but I mean, the wind of the progenitor usually blows away everything what you have around from the interstellar medium. But of course, it will be important at later stages. For example, in Cas A, you see some asymmetries, which probably are due to some inhomogeneity. You have probably some clump on one side, which makes the reverse shock, which propagates inward, so it doesn't make it asymmetric, but very displaced. So the center of the reverse shock and the forward shock are displaced. And this looks like this because you have probably a strong interaction with some higher density material on one side. And then it comes. So in the time scale of hundreds of years, it starts to become very important.
What is, how do you use this kind of simulation to estimate a core? So, like where you have, instead of progenitor star, like a red channel, you just have the core collapse, more or less cold and empty, more or less empty space. This is related to one of the previous slides where you were showing, this one. You were showing the first expansion. Imagine there is nothing there. And the question I was wondering is related to something else, which is the relativistic component. To what extent you need GR? I wonder if there is nothing there, then the initial shock will be fast.
Sure. So
and then maybe is this code what is you mentioned briefly? It's at the beginning that you have some GR correction.
Exactly. So we have a 3-dimensional Newtonian potential, but we have a 1D correction to emulate the neutron star in the center. So this is empirically fitted to the GR of a spherically symmetric neutron star in the center, which of course changes the space-time. And for the projects we are looking at, it's very nice. It works perfectly fine. So this is really nicely included here, and it's important. If you don't treat it, the explosion will be different. You really see quantitative effects of this. So if you don't have anything in the center, the explosion will be very different.
You don't have to material outside. So the remnant will be very different because you don't have all this.
Sure. Also, I don't see a method how you would make the explosion, because you need the neutrinos from the central part. Without the neutrinos, you will not revive the shock unless you have some strange mechanism which gives you the additional energy. I would not understand how you could make the shock expand. So you need to have some explosion which gives you the energy. So I could not imagine if you don't have the proto-Newton star in the center. I don't know what could cause the explosion.
No. I was thinking that you do have to start in the
Okay.
center, but you don't have the outside stuff.
Okay, that's
empty outside. You are at this stage.
okay. Yeah. So
at the second stage.
Exactly. Yeah, but that's
Then,
I think related to Konstantino's question. That this would have influence. Yes, it looks different. You keep much more of these large scales. You don't go to maybe you may not go even to strong Rayleigh-Taylor fragmentation. You may have some very strong clumps here. So I don't have a plot of this here, but it looks a little bit. If you go here to this model, so you will have like these kind of clumps. They're not so fine structured and they're not so fast, so different. But you will have like these kind of structure where you have like maybe here something, and here something, and it will be different.
but would this be observable? And make a prediction or remnant that comes from that?
Prediction is hard to say because we don't understand enough yet, I would say. I mean, we have now maybe dozen or maybe 2 dozens of blue supergiant models. We are now simulating the same amount of red supergiant models, want to compare them. But before we don't understand the difference between these things, we cannot go to understand what's happening if you have like these kind of stripped envelopes. I mean, we have some models of this, but we don't have the systematic set. That's why I would say to make some prediction is a bit hard. Because also how you form these clumps is a bit stochastic, depends on how you make the explosion. And then to make prediction, we also need to understand a bit more the progenitor, if you have like convection in the progenitor, how this would influence on the others, which in the models you're suggesting would not be the case because you would not have these outer layers. But there's a lot of things we need to understand still. But I think, yes, there will be some possibility to say that probably this comes from a model which is stripped.
One last question.
Yeah, I'm in contact with groups now who would like to simulate also what happens if you have very asymmetric interstellar medium and stuff like this, what happens in these cases. So that's exactly what, there's a collaborations going on in that direction. Yeah. This will be very interesting. And it will also be interesting to see what happens maybe is formation of molecules and thus they need some additional physics and understand better, or even chemistry, not physics, also chemistry to understand what's happening. But that's something we cannot do. It's like too much what you would need to include. So that's what other people, other groups have to do. But we provide this data also to people calculating spectra. There's some group in Stockholm who will be doing this and molecules and stuff like this.
Okay, thank you. We can thank Mikael again. Very nice.
I have some questions. Sure. So